How can a universe that is only about 13, 8 billion years old, contain regions that are now roughly 46 billion light-years away? At first, the numbers seem impossible. If light is the fastest thing in nature, and the universe has existed for less than 14 billion years, then surely nothing we can see should be farther away than about 14 billion light-years. Yet when astronomers describe the observable universe, they speak of a sphere nearly 93 billion light-years across. The contradiction is only apparent, but understanding why takes us into one of the strangest ideas in modern physics. Space itself is not fixed. It changes. It stretches. And while ancient light has been travelling toward us, the universe through which that light moves has been quietly growing larger. Before we go farther, tell me what time it is where you are, and where in the world you're listening from tonight. To understand this puzzle, imagine something much simpler than the universe. Picture yourself standing beside a perfectly straight road. A tiny lamp is placed 1 mile away, and when it switches on, its light begins travelling toward you. If the road remains unchanged, calculating the distance is easy. You know how fast the light travels. You know how long it has been moving, and therefore you know how far away the lamp was. This everyday logic works beautifully when the space between objects stays essentially fixed. It is the same logic we use for sound, cars, airplanes, and almost every ordinary journey. But the universe refuses to behave like an ordinary road. On the largest scales, the distance between widely separated regions can change while light is still travelling between them. That distinction is the doorway into modern cosmology. When astronomers say that the universe is about 13, 8 billion years old, they are talking about elapsed cosmic time since the hot, dense early state commonly described by the Big Bang model. This does not mean the universe exploded outward from one central point into some larger empty room. Instead, according to our best cosmological description, the universe itself evolved from a much hotter and denser condition. Space expanded everywhere. There was no unique centre from which all galaxies flew outward. From almost any galaxy today, the large-scale pattern would look broadly similar. Sufficiently distant galaxies would appear to be receding as the distances between cosmic regions increase. Now consider the phrase light year. Despite the word year, a light year is not a measure of time. It is a measure of distance. The distance light travels through a vacuum in 1 year. Roughly 9 trillion miles, or about 46 trillion kilometers. Light moves extraordinarily fast, nearly 186,000 miles per second. Even so, the universe is so enormous that light needs years, millions of years, or billions of years to cross cosmic distances. When you see the sun, you see it as it was roughly 8 minutes ago. When you look at the Andromeda galaxy, you see light that began its journey around 5 million years ago. Looking outward into space is therefore also a way of looking backward in time. This fact gives us our first intuitive limit. If the universe is around 8 billion years old, then we cannot receive light that has been travelling toward us for 20 or 30 billion years. There simply has not been that much cosmic time. The oldest electromagnetic radiation we can directly observe began its free journey somewhat less than 8 billion years ago. After the early universe cooled enough for light to travel through space without constantly scattering from charged particles, we detect that ancient glow today as the cosmic microwave background. It reaches us from every direction, forming something like a faint luminous boundary around the observable universe. Though it is not a physical wall, and certainly not the edge of all existence, if we stopped our reasoning there, we might conclude that the sources of the oldest light should now be approximately 8 billion light-years away. And this is where the puzzle begins. During the entire time that ancient radiation was traveling toward us, the cosmic distance between different regions was not frozen. Space continued expanding. The matter that emitted or last scattered that ancient light was once much closer to the region that would eventually become our location. But while the photons crossed the cosmos, the scale of the universe increased. By the time those photons arrived at our telescopes, the present-day distance to the matter associated with their origin had grown enormously. A useful picture is a sheet of soft, elastic material covered with dots. Imagine 2 dots on this sheet, with a tiny ant walking from one toward the other. The ant moves at a steady speed relative to the material beneath its feet. But while it walks, the sheet itself is slowly stretched. The ant may spend 10 minutes traveling. Yet, when it finally reaches the destination, the place where it began could be much farther away than the distance the ant could have covered on an unstretched sheet. Nothing mysterious happened to the ant's own speed. The distance changed because the surface across which it travelled changed while the journey was taking place. No analogy is perfect, and the universe is not literally an elastic sheet. Still, this image captures something essential. Light always moves locally at the speed of light through empty space. It does not become tired, slow down, or secretly exceed its own speed limit. Yet the large-scale distance between faraway locations can evolve while the light is in transit. That is why the travel time of a photon and the present distance to its source are not necessarily the same number expressed in different units. In an expanding universe, there are several meaningful ways to define cosmic distance, and they do not all agree because they answer different questions. One question is simply, how long has the light been travelling? Another is, how far away was the source when that light was emitted? A third is, how far away would that source be from us now? According to a particular cosmological definition of simultaneous distance, these sound almost identical in ordinary life. Across cosmic scales, they become dramatically different. A galaxy whose ancient light has travelled toward us for more than 13 billion years may now be tens of billions of light years away. We are seeing that galaxy not where and when it exists in our present cosmic era, but as it appeared when the universe was very young. This difference between seeing an object and knowing its present distance is easy to overlook because vision always feels immediate. When you look at a nearby tree, the delay caused by the travel time of light is so tiny that it can safely be ignored. Even the moon is seen only about 3 seconds in the past. The sun appears roughly 8 minutes old to us, but this delay rarely affects daily thought. Once we begin observing distant galaxies, however, the delay becomes fundamental. A telescope is not simply an instrument for looking far away. It is a machine for collecting messages sent from earlier versions of the cosmos, sometimes from epochs before the Sun, Earth, or even our galaxy in its present form existed. The deeper we look, the younger the universe appears. A galaxy whose light took 10 billion years to reach us is shown to us as it was 10 billion years ago. We cannot point a telescope at that same galaxy and see what it is doing right now in the ordinary sense. Whatever light it is emitting in its current state may require billions of additional years to reach our region, assuming the structure of cosmic expansion allows that future light to reach us at all. This creates a remarkable separation between the universe as we observe it and the universe as it may exist at this moment on distant scales. Astronomy always receives the cosmos through layers of delayed information. The number often quoted for the radius of the observable universe, roughly 46 billion light-years, refers to a present-day cosmological distance to the most distant regions whose ancient light can now reach us. Double that radius, and the observable universe is about 93 billion light-years across in terms of present-day distance. The precise value depends on the cosmological parameters used, but the central idea is robust. We are not claiming that a beam of light has travelled 46 billion light-years during 8 billion years of time. Instead, we are saying that the regions from which the oldest observable signals originated are, according to our model of cosmic expansion, now about 46 billion light-years away. This is possible because the expansion rate of the universe has not remained constant throughout cosmic history. The cosmos passed through different eras in which radiation, matter, and later the influence associated with dark energy affected how expansion changed over time. In the early universe, distances between locations evolved differently from the way they do today. To reconstruct present cosmic distances, astronomers use the equations of general relativity together with measurements of expansion history. They study patterns in galaxies, exploding stars, the cosmic microwave background, and other observations. From these clues, they infer not just where objects appear to be, but how the geometry of the universe evolved while their light was travelling. One of the most important clues is cosmological redshift. Light can be thought of as a wave, with a wavelength that determines where it lies in the electromagnetic spectrum. As the universe expands, light travelling across vast cosmic distances is stretched along with the changing scale of space. Its wavelength becomes longer. Visible light may shift toward the red end of the spectrum, while radiation emitted in other wavelength ranges can be shifted even farther. Astronomers measure this stretching and describe it using redshift. In general, larger cosmological redshift indicates that the light comes from an earlier era when the universe was smaller, although translating redshift into distance requires a model of cosmic expansion rather than a simple straight-line formula. This stretching of light gives us a quiet physical record of cosmic history. A photon arriving at a detector today may have begun its journey with a wavelength much shorter than the one we measure now. During billions of years of travel, the expanding universe increased that wavelength. The photon carries evidence of the changing cosmos inside its observed frequency. In this sense, expansion is not merely a theoretical idea invented to explain distant galaxies. Its effects are woven into the light we receive. Every extremely redshifted galaxy is sending us a message not only about stars and matter in the distant past, but also about the changing geometry through which that message travelled. There is another subtle point hidden inside the original question. Asking whether the universe is larger than it is old compares two quantities that do not naturally have the same units. Age is measured in years. Size is measured in light years. We can make the comparison because a light year is defined using the distance light travels in 1 year. In a static universe, that connection might encourage us to think that a universe 13 billion years old should have an observable radius of roughly 13 billion light years. But relativity does not require the geometry of the universe to remain static. Once expanding spacetime enters the picture, the simple relationship between age and present distance disappears. The surprise, then, comes partly from trying to apply ordinary motion to an extraordinary geometry. We imagine galaxies racing through a fixed cosmic arena, with light attempting to cross the same unmoving stage. But general relativity gives us a different picture. Matter and light inhabit space-time, and the geometry of space-time can evolve. On small scales, gravity can hold systems together. Atoms do not expand with the universe, nor do people, planets, solar systems, or even gravitationally bound galaxies. On sufficiently large scales between galaxy groups and clusters, however, cosmic expansion becomes the dominant pattern. The vast separations themselves change with time, and so the universe can be about 8 billion years old, while the observable region has a present radius of roughly 46 billion light-years. The two numbers describe different aspects of the same history. One measures how much cosmic time has passed. The other depends on how distances evolved during that time. There is no need for light to break its speed limit, and no need for the universe to be older than we think, simply because distant regions are now more than 8 billion light-years away. The apparent contradiction dissolves once we allow space to have a history of its own. But this answer opens a deeper mystery. If space can grow while light moves through it, Then what exactly does it mean to say that a galaxy is moving away from us? Can distance between two regions increase faster than light without violating relativity? And if the expansion of space can carry distant regions away so rapidly, how did their light ever manage to reach us in the first place? To understand the true size of the observable universe, we must follow a photon across a cosmos that refuses to remain still. Imagine a single photon leaving a very distant region of the young universe and beginning the long journey toward the place where Earth will one day exist. At first, the distance may seem manageable. The universe is much smaller. Galaxies are closer together in the large-scale sense, and the photon moves faithfully at the speed of light. Yet the road ahead is changing beneath it. While the photon travels, the universe expands. Regions that were once separated by modest distances become farther apart. The photon is always moving locally toward us, but the total distance it must cross is not fixed. In a strange way, its destination can be receding even while the photon is making progress toward it. To understand how this works, we need to stop imagining light as crossing a static stage and instead picture it moving through a geometry that evolves with time. A simple analogy can help. Imagine walking toward the front of a very long moving walkway at an airport. Except the walkway is moving backward beneath your feet. You continue walking forward at a steady pace relative to the surface directly under you. If the walkway moves backward slowly, you still make progress toward the front. If it moves backward more quickly, your progress becomes smaller. And if the backward motion changes with time, your total journey becomes difficult to describe using only your walking speed. Cosmic expansion is not literally a conveyor belt, and galaxies are not being carried through space on a physical surface. But the example captures one important idea. A traveler's local speed does not, by itself, determine how quickly the distance to a faraway destination changes when the space between them is evolving. In cosmology, we often describe this changing geometry with something called the scale factor. You can think of the scale factor as a number that tells us how the large-scale distances between freely moving cosmic locations compare from one era to another. By convention, astronomers usually define its present value as 1. In the past, the scale factor was smaller because the universe was more compact. If the scale factor at some earlier time were 1/2 its present value, then two sufficiently distant locations following the cosmic expansion would have been about half their current separation. This does not mean every object in the universe was physically half its present size. Stars, planets, people, and other gravitationally or electromagnetically bound systems do not simply swell as the universe expands. This distinction between expanding space and expanding objects matters. If cosmic expansion stretched everything equally, your body would grow, atoms would become larger, rulers would expand, and we might never notice the change. Instead, local forces are strong enough to hold many systems together. The electromagnetic attraction inside atoms dominates overwhelmingly over the tiny effect of cosmic expansion at atomic scales. Gravity holds the solar system together and keeps the Milky Way bound. Even our local group of galaxies is gravitationally connected. Expansion becomes important primarily across the enormous voids separating large groups and clusters of galaxies. There, where local binding is weak, the changing scale of the universe becomes visible as a systematic increase in cosmic separation over time. Now, return to our travelling photon. Light moves through space-time along paths that physicists call null geodesics. The phrase may sound technical, but the underlying idea is gentle, in curved or expanding space-time. Light follows the natural paths allowed by the geometry. Locally, any observer passing near the photon still measures its speed as the same constant value, about 299, 792 kilometers per second. Nothing in cosmic expansion changes this fundamental rule, yet the coordinate distance between distant locations can change during the photon's journey. So when we ask how far the photon travelled, the answer depends partly on what kind of distance we mean. In an expanding universe, there is no single universal ruler stretching instantaneously from here to a galaxy billions of light years away. This is one reason cosmologists use several different distance definitions. There is light travel distance, which is related to how long a signal has been on its way. There is proper distance, which asks how far away an object would be according to the geometry of the universe at a particular cosmic time. There are also observational measures such as luminosity distance and angular diameter distance, designed to connect theoretical models with what telescopes actually record. These different distances are not mistakes or competing guesses. They are tools for answering different questions. Nearby, they often give almost the same result, at enormous cosmological scales. However, their differences become essential, because expansion has had billions of years to reshape the relationship between time, light, and separation. Consider a galaxy whose light has taken around 12 billion years to reach us. It would be tempting to say that the galaxy is therefore 12 billion light years away. That statement can be useful in a casual sense, but cosmologically it is incomplete. When the light began its journey, the galaxy's proper distance from the region that would later contain Earth may have been much smaller than 12 billion light years. During the journey, the distance between our regions increased. Today, according to the standard cosmological model, that same galaxy can be far more distant than the simple light travel time suggests. The photon did not somehow travel faster than light, nor did it secretly cover its present-day distance in a straight sprint. It crossed a universe whose scale changed continuously beneath its path. The effect becomes even more dramatic when we consider extremely ancient light. The cosmic microwave background that surrounds us today was released when the universe was roughly 380,000 years old. Before that era, the cosmos was hot enough that ordinary atoms could not remain stable. Electrons moved freely among atomic nuclei, and photons scattered repeatedly from those charged particles. The universe was not dark in the sense of lacking radiation. It was filled with intense light, but it was opaque, more like the interior of a glowing fog than a transparent night sky. As expansion continued, the universe cooled. Electrons combined with nuclei to form neutral atoms. Scattering decreased dramatically, and photons were finally able to travel across vast distances. Those photons have been travelling for almost the entire age of the universe. Yet the matter from which that ancient radiation last scattered is now roughly 46 billion light-years away in present-day cosmological distance. When the photons began moving freely, the distance between that matter and our future location was vastly smaller. The expansion that occurred during the journey accounts for the enormous difference. This is perhaps the clearest example of why age and present radius cannot be related by simply multiplying the age of the universe by the speed of light. The journey occurred through changing space-time, not through a motionless container. What we see today is light from a location that has spent billions of years becoming more distant while its ancient signal moved toward us. There is something almost dreamlike about this picture. The microwave photons entering a radio telescope tonight have crossed nearly all of observable cosmic history. They began travelling freely before stars like the Sun existed, before planets, before galaxies had taken on their mature forms. During their journey, gravity gathered matter into vast filaments and clusters. Generations of stars were born and died. Heavy elements were forged. The Milky Way evolved. The solar system formed. Earth cooled. Oceans appeared. Life emerged. And eventually beings capable of building detectors began measuring those ancient photons. Yet throughout all of this, the photons simply followed the geometry of space-time, their wavelengths stretching as the universe expanded around them. That stretching provides another way to understand the changing cosmic scale. Imagine drawing a wave on a flexible strip of material. If you stretch the strip, the peaks of the wave move farther apart. Something broadly analogous happens to light travelling through an expanding universe. Its wavelength grows in proportion to the changing cosmic scale. A photon that began with a short wavelength may arrive with a much longer one. For the cosmic microwave background, the effect is extraordinary. Radiation that once belonged to a hot universe, thousands of degrees in temperature, has been stretched into microwaves corresponding to a background temperature of only about 7 Kelvin today. The universe itself has cooled in large part because expansion has diluted matter and stretched radiation to lower energies. Cosmological redshift therefore tells us about more than the motion of individual galaxies. In ordinary situations, redshift can be caused by the Doppler effect, as when a source moves away and its waves arrive stretched. But, at cosmological distances, the deeper interpretation involves the expansion of the universe during the light's journey. The greater the expansion between emission and observation, the greater the cosmological redshift. Astronomers express this with a number called z. A redshift of 1, for example, means the observed wavelength has become twice the emitted wavelength. Very distant galaxies can have much larger redshifts, allowing us to see them as they existed when the cosmic scale factor was only a fraction of its present value. There is an elegant relationship hidden here. If a galaxy is observed at a redshift of 3, then the universe's scale factor, when that light was emitted, was about 1/4 of what it is today. The wavelength has been stretched by roughly the same factor by which cosmic scale increased during the light's journey. This gives astronomers a way to connect what arrives at a telescope with the history of expansion. But redshift alone does not immediately give a unique distance without additional knowledge. We must know how quickly the universe expanded at different times. That history depends on its contents: radiation, matter, dark matter, and the component we call dark energy all influence how expansion evolves. The early universe behaved differently from the universe today. Very early on, radiation made a major contribution to the cosmic energy density. Later, matter became dominant. The gravitational attraction associated with matter tended to slow the expansion, although it never reversed the overall expansion in our observed universe. Several billion years ago, the situation changed again. Observations indicate that expansion began accelerating, an effect attributed in the Standard Model to dark energy, often represented mathematically by a cosmological constant, because the expansion rate changes with cosmic time. Calculating the distance to a distant galaxy is more like reconstructing a long journey across a road whose lengthening rate has varied repeatedly than measuring a simple trip along an unchanging highway. We can imagine watching our photons progress using a special kind of cosmic map. Instead of drawing ordinary space alone, we draw cosmic time upward and distance sideways. The photon begins far away and traces a path toward us. Meanwhile, the region that emitted it follows the general expansion and moves to greater proper distance. Early in the photon's journey, something surprising can happen. The proper distance between the photon and us may initially increase, even though the photon is locally travelling in our direction. Expansion can add distance faster than the photon removes it. Later, as our conditions change, the photon may cross a boundary where its forward progress finally wins. From that moment onward, its proper distance to us begins to shrink until it eventually arrives. This idea explains one of the most counterintuitive facts in cosmology. Some of the light reaching Earth today was emitted by regions that were receding from us faster than light, according to a particular cosmological measure of recession. This does not violate special relativity, because the rule forbidding faster than light motion applies locally to objects moving through space-time. Cosmological recession is not quite the same thing. It describes how the distance between widely separated regions evolves as space-time itself expands. Two sufficiently distant galaxies can have a rate of increasing separation greater than the speed of light without either galaxy locally rushing past nearby space faster than a photon. The difference sounds subtle because our intuition was shaped in a world where space-time curvature and cosmic expansion are almost invisible. On Earth, when two cars separate at 100 kilometers per hour, their increasing distance is caused by the cars moving through a nearly fixed environment. Cosmological recession is described differently. Galaxies that are following the large-scale expansion can remain approximately at rest relative to their local surroundings, while the amount of space between widely separated regions increases. This is why simply adding velocities in the ordinary way fails at extreme distances. General relativity replaces our familiar picture with one in which geometry is active, and measurements of distance depend on how space-time is sliced into space and time. None of this means that space is a mysterious substance flowing outward, or that the universe is expanding into an empty exterior. The standard cosmological description does not require an outside region into which our universe grows. Expansion means that the mathematical distances defined within the universe change with time. A two-dimensional analogy is the surface of an inflating balloon. Creatures living only on the surface could observe every distant point, moving away as the surface expands, without needing to travel across the third dimension themselves. From their internal perspective, the surface simply grows. Our three-dimensional cosmic space is not literally the surface of a four-dimensional balloon, but the analogy reminds us that expansion can be an intrinsic property of geometry. And once we become comfortable with that idea, the original size puzzle begins to feel less impossible. A universe does not need to be 46 billion years old for a visible region to be 46 billion light-years away today. It only needs enough time for light to travel from an initially closer region, while cosmic distances increase during the journey. The age tells us the duration of the history. The present distance tells us what expansion has done to the geometry during that history. These are related quantities, but they are not interchangeable. Their relationship contains information about the entire evolution of the cosmos. Perhaps the quietest way to picture it is to imagine the universe as a story written on pages that slowly widen while the words are being read. The photon moves from one word toward another at a perfectly consistent local speed. Yet the page beneath the journey changes its scale. By the time the message arrives, its starting point can lie unimaginably far away. And this leads naturally to the next question. If cosmic distances can grow so rapidly that some regions recede faster than light, then what exactly is Einstein's speed limit protecting? To answer that, we must look more closely at the boundary between motion through space and the expansion of space itself. The idea that distant galaxies can recede from us faster than light sounds. At first, like a direct violation of Einstein's relativity, we are taught that nothing can move faster than light, and that this limit is one of the deepest rules in physics. So how can cosmologists calmly describe galaxies whose distance from us increases faster than a beam of light could cross the same distance? The answer lies in a distinction that is easy to say but takes time to fully feel. Einstein's speed limit applies locally. It governs how objects move through space-time when compared with nearby observers. Cosmic expansion, by contrast, concerns how the geometry between widely separated regions changes. A distant galaxy can become separated from us at a rate greater than the speed of light, without that galaxy locally racing through its surrounding space faster than light. Special relativity was developed for situations in which space-time can be treated as essentially flat and where gravity is negligible. In that setting, observers moving at different constant velocities can disagree about distances and time intervals, yet they all measure the same speed of light in a vacuum. No massive object can be accelerated through local space to the speed of light, because doing so would require more and more energy as its speed approached that limit. Light itself follows the limiting paths of space-time. These principles remain true in cosmology. If a spacecraft passed near a distant galaxy, that local observer would never watch the galaxy streak past faster than light in the ordinary sense. The apparent faster-than-light recession emerges only when we compare objects separated by enormous regions of expanding space-time. General relativity extends Einstein's ideas by allowing space-time itself to be curved and dynamic. Matter and energy influence geometry, and geometry influences how matter and light move. In the universe as a whole, this means space does not need to remain static. The equations permit a cosmos whose large-scale distances evolve with time. When cosmologists describe expansion, they usually imagine a network of observers who move with the average cosmic flow. Each observer is locally at rest with respect to nearby matter, but the distance between far-separated observers increases as the scale factor grows. No individual observer needs to move rapidly through local space. Yet if two observers are sufficiently far apart, the rate at which their proper distance increases can exceed the speed of light. For nearby galaxies, there is a simple approximate relationship known as Hubble's law. The farther away a galaxy is, the faster its recession tends to appear on large scales. In its simplest form, recession speed is approximately equal to the Hubble parameter multiplied by distance. At modest cosmological distances, this relationship works well as an intuitive guide. If one galaxy is twice as far away as another, its recession rate due to expansion is roughly twice as large. Extend that pattern far enough, and eventually the calculated recession rate becomes equal to the speed of light. Beyond that characteristic distance, the recession rate can be greater than light speed. This boundary is sometimes associated with the Hubble radius, though it is not the same as the edge of the observable universe. That difference is important. It would be tempting to imagine the Hubble radius as a wall beyond which light can never reach us. But the universe is more subtle. The Hubble parameter changes over cosmic time, so the distance at which recession equals the speed of light also changes. A photon emitted beyond the Hubble radius can, under the right circumstances, still reach us eventually, early in its journey. Its proper distance from us may even increase, because cosmic expansion is adding separation faster than the photon can locally reduce it. As the expansion history evolves, however, the Hubble radius can change in such a way that the photon eventually enters a region where it begins making net progress toward us. Billions of years later, it may finally arrive. Imagine once more a traveller trying to walk toward you on a surface that is stretching. At every moment, the traveller takes steps in your direction, but if the surface between you is stretching quickly enough, your separation can initially grow. The traveller is not walking backward. The environment is changing faster than the traveller can overcome. Later, if the stretching slows relative to the traveller's progress, the separation begins to shrink. This is broadly similar to what happened to some photons we observe today. Their local motion was always toward our region, yet the distance between them and us initially increased. Only later did the evolution of cosmic expansion allow their journey to turn into a net approach. This is one reason statements like, "that galaxy is moving faster than light," need careful interpretation. In ordinary language, speed sounds absolute, as though there were a single cosmic ruler and clock that everyone could use. General relativity removes that simplicity. Comparing velocities of distant objects in curved or expanding spacetime requires choosing a way to define distance and simultaneity. Different coordinate systems can describe the same physical universe in different mathematical language. Locally measured quantities remain unambiguous, but distant recession speeds are partly tied to how we construct our cosmic map. What does not depend on coordinates is the observable pattern. Distant galaxies are increasingly redshifted. The large-scale universe expands, and the geometry described by our best cosmological models evolves over time. Cosmologists often use a system of coordinates in which galaxies following the general expansion retain nearly fixed spatial coordinates while the scale factor grows. These are called co-moving coordinates. Imagine drawing dots on a rubber sheet before stretching it. The numerical positions of the dots on your original grid could remain unchanged even though their physical separation increases as the sheet expands. In cosmology, a galaxy that simply follows the Hubble flow can remain at approximately the same moving coordinate while its proper distance from us increases. This mathematical choice is extremely useful because it separates the expansion of the universe from smaller local motions, such as galaxies drifting within clusters or stars orbiting within galaxies. Proper distance, by contrast, tries to describe the physical separation between two co-moving locations at a chosen cosmic time. If the co-moving coordinate remains fixed while the scale factor increases, then the proper distance grows. This is the distance that can increase at a rate greater than the speed of light for sufficiently remote objects. Again, there is no local violation of relativity. No signal passing one observer locally outruns light. The faster-than-light rate belongs to the changing separation between distant points across a vast region of dynamic space-time. It is similar to how two extremely distant points on an expanding grid can separate rapidly, even though neither point is moving across the grid in its own immediate neighborhood. This distinction also helps explain why expansion does not pull apart the Earth, the solar system, or the Milky Way. The cosmological solution describes the universe when matter is smoothed over very large scales. On smaller scales, gravitationally bound structures behave differently. The Sun and Earth do not simply follow the Hubble flow because their mutual gravity dominates over the tiny tendency of cosmic expansion at that scale. The same is true of the Milky Way. Even the Andromeda galaxy, about 5 million light-years away, is currently approaching us because the gravity of the local group overcomes the general cosmic expansion between us. Expansion becomes the dominant pattern only across sufficiently large distances where local gravitational binding no longer controls the motion. There is something reassuring in this hierarchy. The universe can expand on enormous scales while local systems remain stable. Your room is not getting larger because of dark energy. The distance between your hands is not increasing because of the Hubble expansion. Atoms are not being stretched into larger atoms. The cosmic expansion we measure is astonishing in total effect, precisely because it operates across such vast distances and such immense periods of time. A tiny fractional change in scale, accumulated over billions of years and billions of light years, becomes one of the defining features of the observable universe. It is a reminder that a process can be almost imperceptible locally, and yet dominate the architecture of the cosmos. Now imagine two galaxies separated by an enormous moving distance. Between them are countless smaller intervals of space. Each small interval expands only modestly, but when we add the expansion of all those intervals together, the total separation can increase extraordinarily quickly. This offers another intuitive way to understand superluminal recession. No small neighboring region needs to expand in a way that locally sends matter or information faster than light. The greater than light recession rate arises from summing the changing geometry across a tremendous distance. Special relativity limits local transmission of information. It does not place the same simple restriction on how fast a global distance, defined across an evolving spacetime, may change. Suppose a galaxy is presently receding from us faster than light. Does that mean we can never see it? Not necessarily. We may already be seeing light that the galaxy emitted long ago, when the history of expansion was different and the distances involved were smaller. In fact, many galaxies we observe at high redshift are now at proper distances where their present recession rate exceeds the speed of light in the standard cosmological description. The light entering our telescopes today was emitted billions of years earlier. What we see is therefore not a report of the galaxy's present condition. It is a preserved image from a much earlier cosmic era, carried to us along a path shaped by the changing expansion history. This creates a beautiful separation between visibility and reachability. An object can be visible to us because ancient light has already entered our region, while signals emitted by that object today may never reach us in the far future. Conversely, there were periods when light from a distant object was initially being carried farther away in proper distance, yet later managed to turn around in the cosmological sense and arrive here. Whether a signal can ultimately reach us depends not simply on the current recession speed of its source, but on the entire future history of the universe's expansion. To determine that, cosmologists must examine horizons rather than relying on a single present-day velocity. A horizon in cosmology is not necessarily a physical object or boundary floating somewhere in space. It is a limit created by the structure of space-time and the finite speed at which information travels. Different kinds of horizons answer different questions. The particle horizon concerns the most distant regions from which light could have reached us since the early universe. The event horizon concerns regions from which signals emitted now or in the future can ever reach us. The Hubble radius marks a scale related to the present expansion rate. These boundaries can have very different sizes and behaviors, even though casual discussions sometimes blur them together. The particle horizon is especially important for understanding why the observable universe is so large. It marks the approximate present-day distance to the most distant regions that have had enough cosmic history to send us information. Because space expanded while that information travelled, the present proper distance to those regions is much greater than the age of the universe expressed in light years. That is how we arrive at a radius near 46 billion light years. We are not looking across 46 billion years of photon travel. We are looking across a geometry that has grown dramatically during less than 14 billion years of cosmic time. The event horizon tells a different and more haunting story. If the universe continues accelerating in a manner similar to what current observations indicate, there are sufficiently distant events whose light will never reach us, even if we wait forever. Space between us and those regions will continue to expand in such a way that their future signals cannot overcome the growing separation. This does not mean those regions suddenly disappear or cease to exist. It means no new information from certain sufficiently remote events can ever enter our future history. The universe can contain places that are visible through ancient light and yet permanently inaccessible through future communication. This might seem like a strange universe, but it follows naturally from general relativity. The speed of light remains sacred in the place where it is meant to apply, local physics. If you stand beside a beam of light, you never measure it moving at anything other than the speed of light in vacuum. If you send a spacecraft past a nearby observer, that spacecraft cannot outrun a photon passing the same observer. Information cannot be transmitted locally through space-time faster than light. What can exceed the speed of light is a cosmological rate of changing distance between remote regions, because that quantity is not the local velocity of one object passing another. It helps to imagine relativity not as a rule telling the entire universe how fast it may grow, but as a rule governing causal contact. Light defines the fastest routes by which one local event can influence another. Those light paths weave a structure through space-time, sometimes called the causal structure. Events outside the region that light can connect to us cannot affect us yet, and some may never affect us at all. Expansion can stretch the separation between distant places enormously, but it cannot allow a local message to leap outside these light-defined limits. In that sense, relativity still protects a deeper order, even in a universe where global distances behave in ways that seem to defy everyday intuition. And perhaps this is the central lesson of faster-than-light cosmic recession. The universe has not broken Einstein's rule. Our ordinary idea of speed was simply too narrow for an evolving cosmos. We are accustomed to movement occurring inside a fixed stage, but general relativity allows the stage itself to change. Once that happens, distance becomes part of the story rather than a passive backdrop. A galaxy can remain locally ordinary, while its separation from us grows at an extraordinary rate. A photon can move toward us while initially getting farther away, and a universe less than 14 billion years old can contain an observable region tens of billions of light years in radius. The next step is to ask where this observable region truly ends. If light has had only a finite amount of time to reach us, there must be a limit to what we can see. But that limit is not the same as the edge of the universe. Beyond it may lie more galaxies, more cosmic structure, and perhaps an expanse far larger than anything we can ever observe. To understand the scale of what is visible, and the even greater mystery of what may lie beyond visibility, we must travel toward the horizon of the observable universe. If you could travel outward tonight, passing the moon, the planets, the nearby stars, and then the galaxies beyond our local group, you would never encounter a glowing wall marked "End of the Universe." The observable universe has a horizon, but that horizon is not a physical border. It is a limit created by time, light, and cosmic expansion. We can see only those regions whose signals have had enough time to reach us during the history of the cosmos. Beyond that limit, there may be more space, more galaxies, perhaps vastly more universe than we will ever observe. The horizon tells us where our information ends, not necessarily where reality ends. And because the universe has been expanding while that information travels, this invisible boundary now lies far farther away than a simple multiplication of age by the speed of light would suggest. The most useful starting point is something called the particle horizon. In cosmology, the particle horizon describes the greatest present-day distance from which any signal travelling at the speed of light could have reached an observer since the beginning of the universe's hot early history. For us today, that distance is roughly 46 billion light-years in every direction. This is why the observable universe is often described as approximately 93 billion light-years across. The word observable can be misleading, because we do not literally see every place within that enormous sphere. Some regions contain matter too faint to detect, and the earliest universe was opaque to ordinary light. Still, the particle horizon provides a fundamental causal boundary. Everything we have ever been able to receive information from must lie within it. It may help to imagine standing in the middle of a dark lake at night. Ripples are travelling toward you from events that happened across the water, but the lake itself has been stretching while those ripples move. The oldest ripple reaching you tonight began when its source was much closer than its present location. As the surface expanded, the source became more distant, even while the ripple continued approaching. Your visible region would therefore be larger than the simple distance the ripple could cross on an unchanging lake. Again, the universe is not literally a stretching surface, but the analogy captures why our particle horizon can now be around 46 billion light-years away, even though cosmic history has lasted only about 13. 8 billion years. There is another layer to this story. Although the particle horizon describes the deepest possible causal reach of our past, ordinary telescopes cannot see all the way back to the earliest moments of the universe. For hundreds of thousands of years after the hot Big Bang, space was filled with a dense plasma of charged particles. Photons constantly collided with free electrons and could not travel freely across great distances. The universe was luminous but fog-like. If you could somehow stand inside that plasma, light would scatter around you again and again, much as visible light is scattered inside a thick cloud. The cosmos had not yet become transparent, so when astronomers look as far back as ordinary electromagnetic radiation allows, they eventually reach not the beginning of time, but the era when this primordial fog cleared. That transition occurred when the universe was roughly 380,000 years old. Expansion had cooled the cosmos enough for electrons and atomic nuclei to combine into mostly neutral atoms. With far fewer free electrons available to scatter radiation, photons could finally move through space across enormous distances. Many of those photons have been travelling ever since. Today we detect them as the cosmic microwave background, or CMB, an extremely faint bath of microwave radiation arriving from every direction in the sky. Its temperature is now about 7 Kelvin above absolute zero. The radiation has cooled because cosmic expansion stretched its wavelengths by an enormous factor during the billions of years between its release and our detectors. When we observe the cosmic microwave background, we are not looking at a spherical object wrapped around the solar system. We are seeing what cosmologists call the surface of last scattering, the distant regions from which the photons reaching us today last scattered significantly before beginning their long, nearly uninterrupted journeys. Because we receive these ancient photons from every direction, the surface appears as a shell surrounding us. An observer in a galaxy billions of light years away would also see a cosmic microwave background surrounding them. Their shell would be centered on their own location, not Earth's. This tells us something profound about cosmic horizons. The observable universe is observer-centered, not because we occupy a privileged position, but because every observer receives information from their own past light cone. A past light cone is a useful way to picture what any observer can know. Imagine your present moment as a point. Now trace backward all the paths that light could have taken to reach you. Nearby events need only a short time to send their signals. More distant events must have happened farther in the past. The farther outward you look, the farther backward in time you see. Eventually, your accessible history narrows toward the young universe. Astronomy is therefore unlike looking across a room, where everything seems to exist at roughly the same moment. A deep image of the cosmos combines many ages at once. Nearby galaxies appear relatively recent. Distant galaxies appear younger. The cosmic microwave background shows the universe before ordinary stars and galaxies had fully formed. This is why the phrase, "the observable universe today," requires some care. We cannot see what distant regions look like today in the same sense that we can see objects in our immediate surroundings. If a galaxy is billions of light years away, the light reaching us tonight left that galaxy billions of years ago. Its present condition is hidden from us behind the finite speed of light. The 46 billion light-year radius refers to the calculated present-day distance to the most distant regions from which information has reached us, not to the distance those regions had when they emitted the light we now receive. What our eyes and telescopes show us is therefore a layered historical record. While cosmological models allow us to estimate how those distant regions would be positioned in the universe at the present cosmic time, this distinction becomes especially important near the cosmic microwave background. The matter associated with the regions we observe in the CMB was much closer to us in the early universe than it is now. While its photons traveled toward us, the scale of the universe increased enormously. Those regions are now tens of billions of light-years away in present-day cosmological distance, and yet the photons themselves have been travelling for less than 8 billion years. Nothing moved locally faster than light to create this result. The distance changed while the photons were moving. The horizon is therefore not a sphere that light simply crossed from its current edge. It is the outcome of the entire expansion history, accumulated moment by moment over almost the whole age of the cosmos. There is also a subtle difference between the particle horizon and the surface of last scattering. The surface of last scattering is the farthest region we can observe directly, using ancient electromagnetic radiation in the conventional sense. The particle horizon lies somewhat deeper in the causal history of the universe because, in principle, information could have travelled during the period before the cosmos became transparent to photons. Ordinary light cannot reveal those earlier times directly, but other messengers may offer partial access. Cosmologists hope that relic gravitational waves or a cosmic background of ancient neutrinos could eventually provide information from epochs earlier than the release of the microwave background. Such measurements are extraordinarily difficult, and some remain beyond present capabilities. But they remind us that the electromagnetic horizon is not identical to the deepest possible horizon of causality. This layered structure of horizons is one reason the word edge can create confusion. An edge suggests that if you somehow crossed it, there would be nothing beyond. The observable horizon means something entirely different. Imagine a sailor on a calm ocean. The horizon marks the farthest surface the sailor can see from that position. But no one imagines the ocean ends there. Travel forward and the horizon changes. New regions come into view while others fall behind. The cosmic analogy is imperfect because the structure of space-time imposes deeper limits than an ordinary visual horizon, but the basic lesson is useful. Our observable boundary describes the limits of information available to us from our location and time. It does not establish a physical boundary to the universe itself. In fact, every sufficiently distant observer has their own observable universe. Two civilizations separated by billions of light years would have overlapping but non-identical cosmic horizons. Each would see some regions the other could not yet see, and each would occupy the center of its own observable sphere. This does not create countless separate universes. It simply reflects the finite speed of information and the fact that observers occupy different positions in space-time. There is no contradiction in every observer seeing themselves near the center of the observable universe. The center is defined by the observer's past light cone, not by a special central location in cosmic space. It is more like everyone standing beneath their own visible sky than everyone claiming to stand at the geographical center of a continent. As telescopes become more powerful, they do not greatly enlarge the fundamental particle horizon. Instead, they allow us to detect fainter and more distant objects within the region already causally accessible to us. A more sensitive telescope can collect photons that previous instruments missed. It can reveal galaxies from earlier epochs, distinguish subtle structures, and measure the universe with greater precision. But no telescope can simply magnify its way beyond a region whose light has not had enough time to reach us. Technology can overcome faintness, blur, atmospheric interference, and detector limitations. It cannot overcome causality. The deepest boundary is not imposed by the size of our mirrors or the sophistication of our electronics. It is written into the history and geometry of space-time itself. This gives deep-field astronomy its quiet sense of time travel. When observatories stare for long periods into apparently empty patches of sky, faint galaxies emerge at enormous distances. Some are seen as they were when the universe was only a small fraction of its present age. Their shapes, colours, and spectra reveal a cosmos still building many of the structures we take for granted today. Yet there is always an observational paradox hidden in the image. The farther away a galaxy appears, the less we know about what it has become since the light departed. A tiny reddish object in a deep field may have evolved dramatically, merged with other galaxies, changed its stellar population, or taken on an entirely different form during the billions of years that its ancient photons were crossing space. The horizon therefore separates not only what is visible from what is invisible, but also knowledge from uncertainty. Within our observable universe, we can test theories against light, particles, and patterns that have reached us. Beyond the particle horizon, we have no direct information today. We can use physical laws and the observed uniformity of the cosmos to infer that the universe probably continues beyond what we see. But we cannot simply inspect those regions. Cosmology is powerful precisely because it combines observation with theory. Yet it also demands humility. A model can tell us what is consistent with the evidence, but evidence from permanently inaccessible regions cannot be collected in the ordinary way. There are boundaries beyond which certainty becomes more difficult. One of the most remarkable observations is that the cosmos near our horizon looks strikingly similar in broad properties in every direction. The cosmic microwave background is extraordinarily uniform, with tiny variations that later helped seed galaxies and clusters. Those minute differences are scientifically precious, because they preserve information about conditions in the early universe. The large-scale uniformity led to deep questions about how distant regions acquired such similar properties, contributing to the development of inflationary cosmology. Cosmic inflation proposes a very brief period of extremely rapid expansion in the early universe, and it successfully addresses several important features of our observable cosmos. Yet details of inflation remain an active field of research, and the precise underlying physics is not known with certainty. Inflation also deepens the mystery of size. If some form of cosmic inflation occurred, the entire universe could be immensely larger than the portion we can observe. Depending on the underlying model, it may be finite but unimaginably vast, or perhaps spatially infinite. Current observations show that the geometry of the observable universe is very close to spatially flat on large scales. But measuring near flatness does not tell us the total size with certainty. A small portion of an enormous curved surface can appear nearly flat, just as a field on Earth looks flat despite the planet's curvature. Our observable region may be only a tiny sample of a much greater whole, and the true scale of that whole remains one of cosmology's unanswered questions. There is a gentle irony here. The farther our science reaches, the more clearly it reveals its own boundaries. We have measured ancient radiation that has travelled through nearly the entire history of the cosmos. We can estimate a visible radius of roughly 46 billion light-years and reconstruct how expansion produced that enormous scale. We can map structures so distant that their light began travelling before Earth existed. Yet none of these achievements tells us with certainty where the universe ends, or whether it ends at all. The horizon gives us an extraordinary sphere of knowledge, but it also surrounds that knowledge with a vast unknown. So when you imagine the observable universe tonight, do not picture a transparent bubble floating inside darkness with a solid boundary around it. Picture instead an ever-deepening archive of arriving signals. Nearby pages were written recently. Distant pages were written billions of years ago. The oldest electromagnetic page comes from the glowing plasma of the young cosmos, while the particle horizon reaches toward an even earlier causal limit. Beyond everything we can currently receive may lie more of the same universe, perhaps extending far beyond our cosmic sight. And this brings us to an even larger question. If the observable universe is only the region whose information has reached us, how large might the entire universe actually be? Once we accept that the observable universe is not necessarily the whole universe, an enormous question opens in front of us. What lies beyond the farthest region we can see? The honest answer is that we do not know. Our telescopes receive information only from within the region that has been able to communicate with us through light or other signals. Beyond that horizon, there may be more galaxies, more clusters, more vast cosmic voids, and more of the same large-scale structure that surrounds us. There may also be features we have never observed directly, but because those regions have not sent us information that has reached Earth, any statement about them must be made carefully, using inference rather than direct observation. The simplest possibility is that the universe continues far beyond our observable horizon, in much the same way it appears to continue within it. This idea is supported by a principle commonly used in cosmology called the cosmological principle. On sufficiently large scales, the universe appears approximately homogeneous and isotropic. Homogeneous means that matter is distributed in broadly similar ways from place to place when averaged over immense distances. Isotropic means that, on those large scales, the universe looks broadly similar in every direction. Galaxies themselves are not evenly sprinkled like dust. Of course, they gather into groups, clusters, filaments, and walls. Yet when we zoom out far enough, the overall cosmic pattern becomes surprisingly uniform. This large-scale uniformity does not prove that regions beyond our horizon are identical to those we can observe. It gives us a reason to suspect that our visible patch is not uniquely special. If physical laws and cosmic structure appear similar everywhere, we can test them. One cautious assumption is that they continue beyond our current view. Still, an assumption is not the same as a measurement. We cannot simply point a telescope beyond the particle horizon and confirm what is there. The horizon is not a technological limitation waiting for a better instrument. It is a limit created by the finite age of the universe and the finite speed at which information can travel. When scientists ask about the total size of the universe, geometry becomes central. General relativity allows space to have different large-scale shapes. A universe can be spatially flat, positively curved, or negatively curved, These words do not necessarily describe the universe as an object embedded in some higher dimensional room. They describe the internal geometry of space itself. In a flat geometry, familiar Euclidean rules work on large scales. Parallel lines remain parallel, and the angles of a large triangle add up to 180 degrees. In curved geometries, those relationships can change. The shape of space affects how distances behave and, potentially, whether the universe has a finite or infinite spatial volume. A positively curved universe is sometimes compared with the two-dimensional surface of a sphere. A sphere has a finite surface area but no edge. A tiny creature living only on that surface could travel in one direction and eventually return to its starting point without ever crossing a boundary. A three-dimensional universe could, in principle, possess a related kind of geometry. It might have a finite total volume while containing no edge at all. Asking what lies beyond it would then be somewhat like asking what lies north of the North Pole while remaining on Earth's surface. The question would not necessarily correspond to another region of ordinary space. A negatively curved universe is often compared with a saddle-shaped surface, though again the real cosmological geometry would be three-dimensional. Such a universe could extend infinitely. Depending on its topology, a spatially flat universe could also be infinite. But flatness alone does not guarantee infinity. There are mathematical ways for a flat space to be finite if its topology connects distant regions to one another. A familiar two-dimensional analogy is the surface of a video game world, where moving off one edge causes you to reappear from the opposite side. Space could theoretically possess non-trivial global connections while appearing locally flat. Whether our universe has any such topology remains unknown. Observations of the cosmic microwave background and other cosmological measurements indicate that the observable universe is extremely close to spatially flat on large scales. This is an important result, but it does not settle the question of total size. Imagine standing in the middle of an enormous plain. The ground beneath you appears flat. Yet this alone does not tell you whether the entire surface extends forever or curves gently on scales much larger than you can see. Earth itself provides a simple example. A small patch of its surface looks almost perfectly flat, even though the planet is spherical. In the same way, our observable region could be a tiny, nearly flat portion of a much larger curved cosmos. If the universe does have noticeable global curvature, its characteristic scale must be very large compared with the region we can currently observe. The closer space appears to flat, the larger the minimum possible curvature scale becomes. But there is an important limit to what this reasoning can achieve. Measurements can constrain curvature ever more tightly. Yet an exactly flat, infinite universe and an enormously large curved universe can look almost indistinguishable within a limited observable patch. There may always be some uncertainty that cannot be removed simply by improving the precision of local measurements, especially if the relevant cosmic scale lies far beyond our causal horizon. This is where early universe physics enters the story again. Many models of cosmic inflation suggest that the region containing our observable universe may have been stretched to a scale vastly larger than what we can see today. Inflation, in its broadest form, describes a period in the very early universe when space expanded extraordinarily rapidly. It was proposed in part to explain why the observable universe is so uniform and why its geometry appears so close to flat. A small region with certain initial properties could have been expanded into an enormous cosmic domain. Our observable universe would then represent only a small portion of that larger inflated region. However, inflation is not one single fully established mechanism with every detail known. There are many inflationary models, and researchers continue to investigate what physical field or process might have driven such an early phase. Some models predict a universe vastly larger than the observable part. Certain versions lead to the idea of eternal inflation, in which inflation continues in some regions while ending in others. These scenarios can produce structures sometimes described as bubble universes or separate cosmic domains. Such ideas are mathematically motivated in some theories, but they should not be presented as confirmed observations. We have no direct evidence that allows us to map or inspect another cosmic domain beyond our own observable region. The possibility of an infinite universe is even more difficult to grasp. Infinity is not simply an extremely large number. It means that no matter how far you travel, there is always more space ahead. If the universe is spatially infinite and roughly homogeneous, there could be an unlimited number of galaxies and stars spread across regions forever beyond our horizon. Yet no observer could survey infinity directly. Every observer would still possess only a finite observable region, because light has travelled for only a finite cosmic time. An infinite universe could therefore contain infinitely more space than any civilization, no matter how advanced, could ever see at one moment. There is something quietly strange about this possibility. The entire cosmic landscape accessible to astronomy, including hundreds of billions of galaxies in the broadest observational estimates and a visible diameter near 93 billion light-years, could still represent effectively zero fraction of an infinite whole. Not a small fraction in the ordinary sense, but no finite fraction at all. Every telescope image, every galaxy survey, every measurement of ancient radiation would belong to one finite patch inside an unlimited expanse. Yet infinity is not required by current observations. The data are compatible with a universe that is simply much larger than the observable region while remaining finite. Cosmologists therefore often distinguish carefully between the observable universe and the universe as a whole. The first can be assigned an approximate present-day size because it is defined by our causal past. The second may not have a measurable total size at all with currently available information. If space is infinite, asking for its total diameter has no finite answer. If space is finite but vastly larger than our horizon, its total dimensions may remain beyond measurement. This is not a failure of science. Science is built around what can be tested from evidence, and sometimes the evidence itself reveals a boundary beyond which direct answers become inaccessible. One possible clue to a finite topology would be repeated patterns in the sky. If space wrapped around on itself on a scale small enough, light might reach us along different paths from the same distant structures. In principle, we might observe multiple images of the same cosmic region or matching patterns in the cosmic microwave background. Researchers have searched for such signatures. So far, no convincing evidence has established that our observable universe wraps around in this way, on scales we can detect. This places limits on certain possible cosmic shapes, but it cannot eliminate every finite topology, especially if the characteristic scale is larger than the observable universe. Another clue comes from the remarkable uniformity of the cosmic microwave background. Regions on opposite sides of the sky have nearly the same temperature, even though, in a simple, non-inflationary picture, they seem too widely separated to have exchanged signals after the hot Big Bang began. This puzzle is known as the horizon problem. Inflation provides a widely studied solution by suggesting that these regions were once close enough to share physical conditions before rapid expansion pushed them far apart. If that picture is broadly correct, then the universe beyond our observable boundary may be enormous, because the same early expansion that explains cosmic uniformity also stretched space far beyond what light has had time to cross since. There is an important difference between something being unobservable now and being unobservable forever. Some regions currently beyond our particle horizon may eventually become visible as more time passes and additional ancient light reaches us. Yet accelerated expansion complicates this picture. Because the universe appears to be undergoing accelerated expansion, there are also regions whose present or future signals may never reach us at all. The observable universe does not simply grow without limit until we eventually see everything. Cosmic horizons evolve, and the future causal structure depends on how expansion behaves over immense spans of time. This means reality may contain events that will never become part of our observable history. Stars may ignite, galaxies may merge, and civilizations might theoretically arise in regions from which no signal can ever reach the Milky Way. Assuming current expectations about long-term acceleration remain valid, those events would still belong to the same larger cosmological model, but they would remain outside our causal future. Science can describe the conditions under which such regions exist, yet no experiment performed here could receive direct news from them. The universe can therefore be larger not only than what we see now, but larger than what we can ever hope to see. Even so, we should be careful not to turn the unknown beyond the horizon into a blank canvas for anything imaginable. The fact that we cannot observe a region directly does not mean every possibility is equally plausible. Known physical laws, cosmological models, and observations within our horizon strongly constrain what we reasonably infer. The simplest expectation is often that large-scale conditions continue in a broadly similar way beyond our observable boundary. More exotic possibilities require additional assumptions or evidence. Scientific humility does not mean abandoning inference. It means clearly separating what has been measured, what is strongly supported, what is plausible, and what remains speculative. There is also a philosophical temptation to ask whether the word universe should mean everything that physically exists, or only the region causally connected to us. In modern cosmology, the observable universe usually refers specifically to our accessible cosmic region, while the universe often refers to the larger spacetime of which that region is part. If multiple disconnected domains exist in some speculative models, the terminology can become even less intuitive. But the language matters less than the principle beneath it. Our observations come from a finite region, while reality may extend far beyond the reach of those observations. Perhaps the most beautiful part of this uncertainty is that we can still learn something about the invisible by studying the visible with extreme care. Tiny temperature variations in ancient microwave radiation, the distribution of galaxies, the brightness of distant supernovae, and the geometry of large-scale cosmic structures all carry clues about the shape and history of space. From a small planet orbiting an ordinary star, we have learned to test the curvature of the universe on scales of billions of light-years. We have not measured the total size of existence, but we have discovered that the visible cosmos does not appear to be a small, closed sphere with an obvious nearby boundary. So how large is the entire universe? The scientifically responsible answer is that we do not know. It is certainly at least as large as the observable region, and observations are consistent with it being much larger. It may be finite on scales far beyond our horizon. It may be spatially infinite. Current measurements cannot choose with certainty between these possibilities. The 93 billion light-year diameter belongs to our observable universe, not necessarily to all of reality. Beyond that, visible sphere may lie an expanse whose true scale cannot be expressed by any measurement we will ever make. And there is a final twist waiting inside this mystery. Even the enormous region we can observe today will not remain equally visible forever. Cosmic expansion is accelerating, and the light arriving from distant galaxies is being stretched to longer and longer wavelengths. Over unimaginably long times, more of the universe will slip beyond effective contact. Future observers may inhabit a cosmos that appears far emptier than ours, with much of today's visible large-scale structure hidden beyond their reach. To understand how the universe can gradually remove parts of itself from view, we must now turn from the unknown space beyond our horizon to the changing horizons of the cosmic future. There is a strange future hidden inside the expansion of the universe. Today, our telescopes reveal galaxies in every direction, spread across enormous cosmic distances. Some are nearby enough to be gravitationally connected to us, while others are so remote that their light has travelled for most of cosmic history. Yet this rich view will not remain unchanged forever. If the accelerated expansion we observe today continues, more and more distant galaxies will eventually pass beyond a horizon from which newly emitted light can never reach us. the galaxies themselves do not suddenly disappear. Instead, the space between us grows in such a way that their future messages are permanently prevented from arriving. The universe can therefore become less observable with time, even while its total history continues. The idea of a cosmic event horizon is closely related to the event horizon around a black hole, but the physical situation is very different. Around a black hole, the horizon marks a boundary beyond which light cannot escape outward, because space-time is curved so strongly. In cosmology, an event horizon can arise because the expansion of the universe accelerates. It marks the greatest distance from which a signal emitted now can ever reach us in the far future. Assuming the expansion history continues in a particular way, this horizon is not a physical shell. You could not fly toward it and find a surface. It is a boundary defined by which events can communicate with us and which cannot. To understand why accelerated expansion changes everything, imagine two distant galaxies with an enormous amount of expanding space between them. If expansion were gradually slowing, a photon sent from one galaxy might eventually make progress across the intervening distance. But if the expansion accelerates strongly enough, the amount of space added between the galaxies can grow so quickly that the photon never closes the gap. Locally, the photon still moves at the speed of light. It does nothing wrong, and no law of relativity is broken. The failure comes from the changing geometry of the journey. The destination is carried away by the evolution of cosmic distance faster than the light signal can overcome in the long run. This distinction leads to an important cosmic separation between what we can see today and what we can ever influence or receive signals from in the future. Some galaxies are visible because their ancient light was emitted when they were much closer in cosmological terms. We may continue receiving older and older information from them for a very long time, yet there can be a last signal from a sufficiently distant region that will ever reach us. Anything emitted there after a certain cosmic time may remain forever outside our causal future. In this sense, visibility is a historical relationship. A galaxy can remain present in our telescopes while its current state has already become permanently inaccessible. The reason this future is taken seriously is the observation that the expansion of the universe is accelerating. In the late 20th century, measurements of distant type-year supernovae revealed that the cosmos was not merely expanding, but that its expansion had begun speeding up. Since then, several independent lines of evidence have supported a cosmological model in which a component called dark energy dominates the present large-scale dynamics. The simplest version treats dark energy as a cosmological constant, an energy associated with empty space whose density remains nearly constant as the universe expands. This model fits a broad range of observations remarkably well, though the deeper physical nature of dark energy remains unknown. The phrase dark energy can sound more mysterious than the evidence requires. It does not necessarily mean that physicists have identified a new substance floating between galaxies. The term is a convenient label for whatever is driving the observed accelerated expansion in our current models. A cosmological constant is the simplest explanation, and so far it remains consistent with observations. Other possibilities have been studied, including forms of evolving energy or modifications to gravity on very large scales. At present, there is no confirmed evidence that a more complicated explanation is required. The uncertainty is real, and because the far future depends strongly on the behavior of dark energy, predictions about the ultimate cosmic horizon always carry assumptions. If dark energy behaves approximately like a cosmological constant forever, then the distant universe will gradually become more isolated from us. Galaxies that are not gravitationally bound to the local group will continue to recede. Their light will be stretched to longer and longer wavelengths by cosmic expansion. A galaxy that is visible today in optical light will eventually appear increasingly redshifted, then shifted into infrared, microwave, and still longer wavelengths. At the same time, its apparent brightness will fade, Eventually, its photons will arrive so rarely and with such low energies that detecting them becomes extraordinarily difficult. Long before any dramatic boundary appears, distant galaxies will simply grow dimmer, rather, and quieter. Our own gravitational neighbourhood will behave differently. The Milky Way and Andromeda are bound to one another and are expected to merge in several billion years. Although the precise details of the merger remain a matter of simulation and measurement, other smaller galaxies in the local group are also gravitationally connected to this system. Cosmic expansion does not pull these bound structures apart under the standard dark energy model. Far in the future, the descendants of these nearby galaxies may form a single large, gravitationally bound system. Beyond it, however, most other galaxy groups will recede so far that their observable light becomes vanishingly faint. For inhabitants of that distant future, the night sky could contain far less evidence of cosmic expansion than ours does today. If they arose after most external galaxies had faded beyond practical detection, they might see only the stars belonging to their own merged galactic system. The enormous cosmic web visible to modern astronomy would be hidden. Distant galaxies would no longer provide an obvious recession pattern. The cosmic microwave background would also be stretched to vastly longer wavelengths and cooler temperatures, eventually becoming extremely difficult to detect against other backgrounds. Some of the clearest evidence we currently possess for the Big Bang and the evolving universe could become inaccessible to ordinary observation. This possibility creates an unusual asymmetry in scientific opportunity. We often imagine that a civilization in the distant future would necessarily know more about the universe because it would have had more time to develop technology. But time can remove evidence as well as provide it. A future astronomer might possess instruments far beyond anything humans can build today, yet the signals they need may simply no longer be arriving in detectable form. They could reconstruct parts of cosmic history from local stars, element abundances, gravitational systems, and perhaps preserved records. But without such records, the broader universe might look fundamentally more isolated. In cosmology, being born later does not automatically mean having access to a larger observational universe. The event horizon also places a limit on possible journeys. If a destination lies beyond the region from which signals sent now can ever reach us, then a spacecraft launched from our location cannot simply chase it indefinitely and expect to arrive. The geometry of accelerated expansion may prevent causal contact altogether, even at speeds arbitrarily close to the speed of light. A traveller cannot overcome a horizon defined by space-time itself. This is not because the spacecraft runs out of fuel or because the destination outruns light locally. It is because there is no future light-like or slower path from here that intersects certain distant events. The structure of the future universe itself determines which places remain reachable. There is, however, no need to imagine a sharp moment when billions of galaxies vanish at once. Cosmic horizons operate gradually in what we observe. Light emitted long ago continues to arrive, increasingly stretched and delayed. A distant galaxy can remain technically visible for an immense period, even after no newly emitted signal from its later history can reach us. In certain cosmological descriptions, we may never watch the galaxy visibly cross the event horizon at a finite moment in our own time. Instead, its image becomes increasingly redshifted and faint. The universe hides its distant regions gently, not by drawing a curtain across the sky, but by stretching their messages toward invisibility. This gradual fading also reveals why horizons depend on the entire future history of expansion, rather than just the expansion rate today. To know whether a photon emitted now will eventually reach us, we must know how the scale factor behaves for all future time. If accelerated expansion continues indefinitely in a cosmological constant-like way, an event horizon persists. If dark energy changes dramatically in the future, the horizon could behave differently. Our observations currently constrain dark energy to resemble a cosmological constant fairly well, but they cannot directly measure its behavior trillions of years from now. Cosmology therefore combines strong present evidence with cautious extrapolation when discussing the remote future. One speculative possibility sometimes discussed is that dark energy might not remain constant. If its properties evolved in particular ways, cosmic acceleration could weaken, strengthen, or change character. Some hypothetical models produce dramatic endings, while others lead to futures more similar to the standard picture. But there is currently no reason to treat any exotic scenario as established fact. The quietest and most conservative projection is based on the cosmological model that best matches current observations: continued expansion, continued acceleration, and increasing causal isolation between unbound regions. Even this relatively simple future is extraordinary enough. We do not need to exaggerate it to feel its scale. As the universe ages, star formation will also decline. Galaxies gradually consume or lose the cold gas needed to create new stars, and the rate of stellar birth has already fallen substantially from its peak billions of years ago. Over unimaginably long periods, existing stars will exhaust their nuclear fuel. The universe will not suddenly become completely dark, because long-lived low-mass stars can survive for extraordinarily long times, and many other physical processes continue. But the bright stellar era is temporary on cosmic timescales. Combined with accelerated expansion, this means the future universe is expected to become not only more isolated but also increasingly quiet and dilute. The scale of this future is almost impossible to fit into human intuition. Civilizations, species, mountain ranges, and even stars occupy tiny intervals compared with the durations involved. Yet the physics can be described with surprisingly simple ideas. Gravity binds local structures, expansion separates unbound ones, and light carries information only where space-time permits it to travel. Over enough time, these modest rules transform the observable cosmos. Galaxy clusters drift beyond contact, their light stretches, the ancient microwave glow fades. The local gravitational island remains while the wider cosmic ocean retreats beyond detection. Nothing needs to rush. The universe changes simply by continuing what it is already doing. There is something deeply valuable about living during an era when so much of cosmic history is still visible. We can observe nearby galaxies in detail and distant galaxies in their youth. We can measure the large-scale expansion and detect the afterglow of the early universe. We can compare stars of different ages, trace the growth of cosmic structure, and infer a history stretching back almost to the beginning of the hot Big Bang phase. Our position in time is not physically privileged, but it is scientifically fortunate. The sky contains records from many eras at once, allowing us to reconstruct a story that future observers may find much harder to recover from nature alone. And so the universe is not merely larger than its age might first suggest. It is also changing which parts of itself can communicate with us. The boundary of what is observable is not frozen, and the boundary of what is reachable is different again. We live inside a space-time whose horizons depend on both its past and its future. Some ancient light has crossed expanding space for nearly 8 billion years to reach us, while some light emitted far away today may travel forever without arriving. Between those two facts lies the full strangeness of an expanding cosmos, a universe whose geometry shapes not only where things are, but which parts of reality can ever share information with one another. That brings us back, finally, to the original question. How can the universe be so young and yet contain an observable region so vast? The answer has led us through expanding space, changing distances, cosmic horizons, and a future in which much of the visible sky slowly fades beyond contact. But the deepest meaning of the question is not really about a number. It is about what distance means inside a universe that has a history. To close the journey, we can now return to those two deceptively simple quantities, age and size, and ask what they reveal about our own small place within a cosmos that may be far larger than we will ever know. We began with a question that seemed almost like a contradiction. How can a universe about 8 billion years old, contain an observable region, roughly 93 billion light-years across? The answer is not that. Light secretly moved faster than light. And not that the age of the universe has been misread by some enormous amount. The answer is that distance in an evolving cosmos does not behave like distance on a fixed road. Space itself changes with time. While light crosses the universe, the scale of the universe grows. So the age of the cosmos and the present distance to the farthest visible regions describe two different aspects of one history. Once this distinction becomes clear, the numbers stop fighting each other. A photon can travel for less than 8 billion years, and still come from a region that is now far more than 8 billion light-years away. The photon began its journey when the distance was much smaller. As it travelled, the space separating its origin from us expanded. By the time the light arrived, the place associated with its emission had become enormously more distant in present-day cosmological terms. The light did not cross the present distance as though it were fixed from the beginning. It crossed a changing geometry. The path stretched, the wavelength stretched, and the meaning of distance evolved along with the universe. This is one of the quiet lessons of relativity. Measurements that seem simple in everyday life can become subtle on cosmic scales. We are used to thinking of space as a silent background, a kind of empty container in which matter moves. General relativity replaces that picture with something deeper. Space and time are part of the physical structure of the universe. They can curve, expand, and respond to matter and energy. The stage is no longer separate from the play. When the universe changes, the geometry in which everything happens changes too. And because our intuition was built among rooms, roads, mountains, and planets, it is not surprising that the largest scales of reality initially feel strange. The observable universe is therefore best imagined not as a fixed ball whose edge marks the end of existence, but as a region defined by communication. It is the part of cosmic history from which information has been able to reach us. Its horizon depends on where we are, when we are, and how space-time has evolved. Another observer, billions of light-years away, would possess a different observable universe centered on their own location. Their cosmic horizon would overlap with ours in some regions and differ in others. No observer is given a view of everything. Every observer receives only the part of reality that can fit inside their own causal past. This changes the meaning of the word far. A galaxy may be far because its present cosmological distance is enormous, but the light we see from it may have been emitted when it was much closer. Another region may be so distant that its future light will never reach us at all. Distance, visibility, age, and reachability are therefore not interchangeable ideas. They are related by the geometry of spacetime, but each answers a different question. Once this is understood, the universe becomes less like a static map and more like a network of possible conversations, some ongoing, some delayed by billions of years, and some permanently impossible. The cosmic microwave background gives us perhaps the most powerful example of this delayed conversation. Its photons began traveling freely when the universe was only about 380,000 years old. Since then, they have crossed almost all of cosmic history. They have passed through a universe in which stars formed, galaxies assembled, planets appeared, and life eventually evolved on at least one small world capable of measuring them. Those ancient photons arrive today as microwaves, their wavelength stretched by expansion. The regions associated with their origin are now roughly 46 billion light-years away. In that single fact, the original paradox is resolved. The light is ancient, but the present distance is larger because the universe grew while the light travelled. And even that horizon does not tell us how large the entire universe is. The observable region is only the part we can receive information from. Beyond it, space may continue for an enormous but finite distance, or it may continue without end. Current observations show that the large-scale geometry of our observable region is very close to spatially flat. But near flatness does not reveal the total size with certainty. An immense curved universe can appear flat over a limited patch. A truly flat universe may be infinite, or it may possess a more complicated finite topology. The evidence gives us important limits, but it does not yet give us a final map of all existence. There is a natural human discomfort in that uncertainty. We like boundaries because boundaries make things easier to picture. A room has walls. A country has borders. A planet has a surface. Even a galaxy has a recognizable structure. But the universe may not offer us a simple outer edge. It might be finite without a boundary, or infinite without any final destination. And because our observations are limited by causality, there may be no experiment capable of measuring the total size if the relevant scale lies far beyond our horizon. This is not a defect in scientific thinking. It is one of the places where science most clearly teaches us to distinguish between what can be known, what can be inferred, and what remains open. The future adds another layer of humility. If accelerated expansion continues, distant galaxies will gradually fade from effective contact. Their light will stretch toward longer wavelengths and become harder to detect. Regions that are visible through ancient signals may be unreachable through future ones. The cosmic microwave background itself will continue to cool and redshift. Far future observers may live in a gravitationally bound island, surrounded by a sky that appears much emptier than ours. They may possess more advanced instruments, yet fewer cosmic messages will remain available. Knowledge does not depend only on intelligence. It also depends on when in cosmic history an observer happens to exist. In that sense, we live during a remarkable astronomical era. The universe is old enough for heavy elements, rocky planets, complex chemistry, and intelligent observers to exist, yet young enough that the sky still carries information from a vast range of cosmic distances. We can see nearby galaxies and distant galaxies in their youth. We can measure ancient microwave radiation and trace structures extending across billions of light years. We can compare different epochs simply by looking outward. There is no reason to call our era cosmically special in a mystical sense, but it is scientifically generous. Nature has left many pages of its history open to us at the same time. What makes this especially striking is the scale of the creature doing the measuring. A human body is a little over a meter in size. A human lifetime is usually measured in decades. Our entire recorded scientific history occupies only a tiny instant compared with cosmic time. Yet using mathematics, telescopes, detectors, and careful reasoning, beings of this scale have learned to estimate the age of the universe, measure its expansion, map the cosmic microwave background, and infer distances tens of billions of light years away. We cannot physically cross most of these distances, but information can reach us, and thought can travel farther still by reconstructing the laws that shape the journey. There is something calming in this contrast. Our lives feel immediate because they unfold at human scales, where minutes matter and familiar distances seem large. But above us is a universe whose light has been travelling for billions of years without hurry. Galaxies separate over intervals too long for any person to witness directly. Stars are born and die across spans that dwarf civilizations. The cosmic horizon itself changes with the slow evolution of space-time. Nothing in this larger story is rushed. The universe does not need to finish its transformations quickly. It simply continues, following physical laws one moment at a time, while enormous consequences emerge from changes that can be almost invisible locally. Perhaps this is also why the original question feels so satisfying when it is finally understood. Is the universe larger than it is old? Sounds like a puzzle about numbers. But underneath it is a lesson about assumptions. The apparent contradiction exists only if we imagine a static universe in which light crosses fixed distances. Once we replace that picture with expanding space-time, the puzzle dissolves. The age remains about 13, 8 billion years. The observable radius can still be roughly 46 billion light-years. Both statements can be true because cosmic distance has a history. The universe is not required to fit inside the simple geometry our everyday intuition expects. And the answer does not close every mystery. It opens deeper ones. We still do not know the true nature of dark energy. We do not know whether cosmic inflation happened exactly as our leading models describe, or what fundamental physics drove it. We do not know whether the entire universe is finite or infinite. We do not know whether regions beyond our horizon resemble ours in every meaningful way. Science has given us a remarkably successful description of the observable cosmos. But the edge of observation remains an edge of certainty. There is always a difference between the universe we can model and the full reality that may lie beyond our ability to receive information. Yet uncertainty does not make the picture empty. It makes the confirmed part more extraordinary. We know that the universe has expanded. We know that looking into deep space means looking into the past. We know that ancient light has been stretched by the changing cosmic scale. We know that the observable universe is much larger in present-day distance than its age expressed in light years. We know that space-time geometry can create horizons without violating the local speed of light. These are not guesses invented to fill an unknown darkness. They are conclusions built from observations that agree across many independent lines of evidence. So if you imagine the universe now, perhaps picture it not as a giant sphere with a number written across its diameter, but as a living geometry filled with delayed messages. Every distant photon carries a fragment of an earlier cosmos. Every redshift contains evidence of changing scale. Every horizon marks the limit of a possible connection. Some signals began their journeys before the Earth existed. Others being emitted today will never arrive here. We inhabit one small region within this immense web of causality, receiving a thin but precious stream of information from times and places we can never visit. And somewhere beneath all these enormous distances is a simple fact. We are part of the same universe we are trying to understand. The atoms in our bodies were shaped by earlier generations of stars. The laws governing light in distant galaxies are the same laws that allow light to enter our eyes. The space-time whose expansion carries galaxies beyond our reach is also the space-time in which every quiet human moment unfolds. There is no separation between the observer and the cosmos in that deeper sense. We are not looking at the universe from outside. We are one small process occurring within it, briefly able to notice the larger pattern. Tonight, the oldest light in the sky is still arriving. Distant galaxies continue to send us images of a past that no longer exists in quite the same form. Beyond our horizon, the universe may continue farther than any measurement can ever reach, and far into the future. Some of what we see now may fade beyond contact, but for this moment, the cosmos is open enough for us to read part of its story. Its age and its size no longer need to seem contradictory. They are simply two traces of an expanding history, unfolding quietly across space-time, while we rest beneath a sky much larger than it first appears.